In this video, we'll take a look at the chain rules for multivariable functions. When you deal with a function of a single variable, the chain rule allows you to differentiate a function that is the composition of two other functions. So recall, if you want to take the derivative with respect to x of f of g of x, that's going to equal to the derivative of the outer function, so f prime of g of x times the derivative of the inner part of our function. Like that. Now, if you're dealing with a function of multiple variables, you do have something similar to this, but with multiple variables, we now bring into play partial derivatives. But it will be very reminiscent of what we see here. So let's begin with a theorem. Let's begin with a function. Let w be a function of two variables, x and y. So w equals f of xy, where f is differentiable. If x is given by some function of t, it's parameterized, so let's say g of t, and y is some other function of t, let's say h of t, where both g and h are differentiable functions of t. These are single variable functions. So here we're g and h are differentiable functions of t. Then w is differentiable. With respect to t. And the way you take the derivative is dw dt is equal to del w del x, so the partial derivative. Notice here we need the partial derivative because this is a function of two variables, times the derivative of x with respect to t. Here notice this is a regular derivative since this is a function of one variable, plus del w del y. Again, w is a function of both x and y, so we need a partial derivative, times the derivative of y with respect to t, because again, y is a function of a single variable t, so we would just take a normal derivative rather than a different partial derivative. The proof of this one is really rather accessible and straightforward without any major trickery or any, where'd you pull that from? So let's begin with f. Let f be differentiable. I guess I should say f of x comma y. So let f of x comma y be differentiable. Well, then what that means is, by definition, the increment of w, right? Because w, where is that? W equals f of x, y. The increment of the function would be the increment of w. That's going to equal to del w del x times delta x plus del w del y times delta y plus epsilon 1 delta x plus epsilon 2 delta y, where delta x, delta y approaching the origin implies that epsilon 1 and epsilon 2 approach the origin. So here I guess I should say by definition, this is true. That's the definition of what it means for the function to be differentiable. Okay, so what do we mean by this expression? Delta W, delta T. Well, then that would be the same as this expression, where everything's being divided by delta T. Okay, so that would give us, let's see, del W, del X over delta T, right? If we're dividing this side by delta T, that means we're dividing this side by delta T. So each of these gets divided by delta T. So that's this times this. Well, if we're dividing by delta T, we're saying this times this over delta T. But since that's just a product, I can either divide the whole thing by that, or I can just say I'm dividing this by that, and that means the same thing. It's like if we were saying, 5 times 10 divided by 2, or if I were saying 5 times 10 over 2. That's the same thing, right? That would be 50 divided by 2 is 25, and here that would be 5 times 5, it's still 25. So same thing here. I'm dividing the whole thing by delta T, which really means I can just say I'm dividing that one by delta T. Plus del W, del Y, delta Y over delta T, plus epsilon 1, delta X over delta T, plus epsilon 2 of delta Y over delta T. Thus, dw dt, which is really just the limit as delta T approaches 0 of delta W, delta T, that's equal to the limit as delta T approaches 0. If this is equal to that, then the limit of this is equal to the limit of that. So it will be the limit as delta T approaches 0 of del W, del X delta over delta T, plus del W, del Y, times delta Y over delta T. Don't know where I got a plus from in there. Over here is plus epsilon 1 times delta X over delta T, plus epsilon 2 over delta X times delta Y over delta T. So here I'm just taking the limit of this side as delta T approaches 0, which is the limit of this side as delta T approaches 0. Oh, but as delta T approaches 0, that is equal to del W, del X times, what's the limit as delta X approaches 0 of delta X over delta T? Well, thinking back to Cal 1, that's the derivative of X with respect to T. So this is del W, del X times dx dt, plus, something over here, that's going to be del W, del Y times dy dt. And since delta T is approaching 0, that means delta X and delta Y are both approaching 0. Oh, but because this is a differentiable function, that means as delta X and delta Y approach 0, that means epsilon 1 and epsilon 2 are approaching 0. So here, as you take delta X approaches 0, this and this both drop to 0. So if you want, you can say that's 0 times the derivative of X with respect to T, or probably better off just not saying anything. And there we go. The derivative of W with respect to T is del W, del X times dx dt plus del W, del Y times dy dt, as we see here. All right, so let's take a look at an example. Let's go ahead and take the following function. W is equal to the natural log of y over x. Now here, these are two functions where x is going to be defined as the cosine of t, and y will also be defined trigonometrically. Y is the sine of t. Now there's two ways to do this. The first way we can do this is we can use this chain rule right here. So let's see how that looks. Well, let's see, that's dw dt. Oh, so the question is find dw dt. I guess I should have started with that, right? Find dw dt. All right, so we can go ahead and do this two ways. We can either use this chain rule. So let's try that first. That's going to be dw dt. That's del w del x times dx dt plus del w del y times dy dt. And we can find all of those things. Here, del w del x, the derivative of the natural log of x over y with respect to the x. Well, let's see. The derivative of the natural log of something is 1 over that something times the derivative of that something. Okay, well, if we're taking the derivative with respect to x, that's a constant over x. And if you take the derivative of a constant over x, you get the negative of that constant over x squared. Like this. So this right here is the derivative of this with respect to x, but now we need to multiply that times the derivative of x with respect to t. Okay, well, that's just the derivative of cosine of t with respect to t, which would be negative the sine of t. Plus, and then we do the same thing, but now with respect to y. Okay, well, again, the derivative of the natural log of something is going to be 1 over that something. But now, by the chain rule, we need to multiply that by the derivative of the inside here. Okay, well, let's see. The derivative of y over x. Now, x is a constant, so really this is just the derivative of y over a constant. Well, it's going to be 1 over the constant. Like that. So that's the derivative of w with respect to y. But now I need to multiply that by the derivative of y with respect to t. Okay, well, the derivative of y with respect to t, that's the derivative of sine of t with respect to t, which is the cosine of t. Here, this simplifies out quite a lot. Dividing by a fraction is the same as multiplying by the reciprocal. So here I can say, okay, this times x over y, and that'll give me negative 1 over x times negative the sine of t, plus here, dividing by y over x, the same as multiplying by x over y. So if I multiply this by x over y, I just get 1 over y times the cosine of t. Okay. Now this might look a little strange because, of course, you're taking a derivative with respect to t, but here it looks like my answer involves both t and the original variables x and y. Oh, but we can substitute. After all, x means cosine of t, and y equals sine of t. So here you can think of this as negative 1 over cosine of t times negative the sine of t plus 1 over y, 1 over sine of t times the cosine of t, which is, well, let's see, double negative makes that a positive. So that'll be positive sine of t over cosine of t, that's tangent of t. And then plus cosine of t over sine of t, well, that's going to be the reciprocal. So that'll be the cotangent of t. And there we go. There's our derivative of w with respect to t, which does not at all look like what you might expect, but, well, here it is. So this is one way to do it. You can go ahead and use the chain rule. You're saying, well, okay, so what's the other way to do it? The other way to do it is to start with a substitution from the beginning. We're going to do the exact same problem. Let's say we have w equals the natural log of y over x, where x is equal to the cosine of t, and y is equal to the sine of t. Okay. We can begin, and the question is find dw dt. Now here, this is a function of two variables, but each of those variables is a function of a single variable. So what that means is we could begin by simply stating, okay, well, w is really equal to the natural log of y can be thought of as the sine of t, over x can be thought of as the cosine of t, which means w equals the natural log of the tangent of t. Oh, but now that's a function of a single variable. which means now I can take the derivative of this as if we were back in Cal 1. Now you might notice that although now we just have a single variable, this function does look a little more complicated than what we started with or what we used over here. So there's a bit of a trade-off. Here, the chain rule requires several components, but each one is relatively simple. By substituting at the very beginning, you're down to a function of a single variable, but now that function may not be as nice as you would hope. So it's not like one way is better than the other. It's a bit of a trade-off. In some cases, doing the substitution early is going to be a lot faster because, yeah, this might get a little less pleasant, but not too bad. Whereas in other cases, this might get huge, in which case you may wish to handle it separately. But both ways will work just fine. So here we're going to say dw dt is equal to, all right, now we're just using the chain rule that we're used to from Cal 1. We're going to take the derivative of this thing. Okay, well, the derivative of the natural log of something is 1 over that something. But now, due to the chain rule from Cal 1, we have to now multiply by the derivative of this inner part. Here, the derivative of tangent is secant squared of t. You may notice that our answer is a bit different here. That one versus this one. Of course, trigonometric functions are expressible in a bunch of different ways. So here you might wonder, how do you get that one then? How does this become this? Or maybe we're wrong. Maybe they're not interchangeable. Well, no. We can simplify this. After all, this is secant squared of t over tangent of t. Okay. Now, secant squared of t, that's one part of the Pythagorean identity. Remember, the Pythagorean identity is sine squared plus cosine squared of theta is equal to 1. An alternate version of that was tangent squared of theta plus 1 equals secant squared of theta. So here this can be separated out as secant squared of t. Well, that's going to be tangent squared of t plus 1 over tangent of t. And now tangent squared of t over tangent of t, that's the tangent of t. Plus the reciprocal, 1 over the tangent of t, well, that's the cotangent of t, which, as you see, is exactly the same result we had before. Cotangent of t plus tangent of t. Cotangent of t plus tangent of t. So in any event, we find our answer. So here, keep that in mind. You can either start by using the chain rule at the start, or if you prefer, you can use substitution and then use just the regular chain rule from Cal 1. Either way, you're not getting away from the chain rule. You kind of just get to choose which one you want to use. Let's go ahead and have you try one of these. Let's say you have a function w, which is a function of the variables x, y, and z. So w equals 3y plus x, xy plus xz plus yz. Where each of these x, y, and z are a function of a variable t. Here x will equal to t minus 1, y is equal to t squared minus 1, and z is equal to just t, like that. So the question is, find the derivative of w with respect to the parameter t. Find dw dt. Remember, you can either substitute this from the beginning and use the chain rule from Cal 1, or you can use the chain rule as we see here at the beginning of this theorem for a multivariable function. And both should give you the exact same answer. So go ahead and give this a try. Pause the video, go through this, and once you're done, go ahead and unpause and we'll confirm this together. Alright, so I'm going to go ahead and do this using the chain rule that we see in this section. If you do it by substitution, that'll also work just fine. But here, I think we should illustrate what's going on in this section. So dw dt, that's going to be the partial of x with respect, the partial of w with respect to x times dx dt, plus the partial of w with respect to y times dy dt. So that's the theorem that we see here. Del w del x dx dt, del w del y dy dt. But here you have a third variable. You have a third function. Well, yeah, but what have we been doing for the last several chapters? The difference between something in the plane or something in space or in 4 dimensions is just follow the trend with another component. So here that would be del w del z times dz dt. So even without being told that, hopefully the pattern becomes obvious because it's largely the same pattern we've been using for a few chapters now. All right, so let's go ahead and do that. Here, del w del x, we want the derivative of this thing with respect to x. Okay, well, the derivative with respect to x of this is y. With respect to x, that'll be z. And with respect to x, that's a constant, so its derivative is 0. So that's just y plus z times, now the derivative of x with respect to t, well, that'll just be 1. Plus, if we want to now take the derivative of w with respect to y, well, with respect to y, that derivative is x. With respect to y, that's a constant, so the derivative is 0. And the derivative with respect to y here is just the coefficient z. So you're left with x plus z. We don't worry about the 0. Times the derivative of y with respect to t. Here, the derivative of t squared is 2t. The derivative of the constant is 0. Plus the derivative, the partial with respect to z of w. Well, with respect to z, that's a constant, so its derivative is 0. And here, that's coefficient times z, and that's coefficient times z. So the derivative of a coefficient times z with respect to z is just the coefficient. So that would be an x plus a y. Times the derivative of z with respect to t. And here, the derivative of t with respect to t is just the number 1. Here, this is our result, but it does look strange considering the fact that we wanted a function of t at the end. Well, this x, y, and z can simply be substituted out for the parameterization as shown. So here that would be t squared minus 1 plus another t. So that's going to be t squared plus t minus 1 times the number 1. Okay, we'll just leave that alone. That's your y plus your z. That gives you t squared plus t minus 1. Plus, over here we want x plus z. Okay, so we're going to add these together. That's going to be t plus another t. That's 2t minus 1. Oh, but we're multiplying that by 2t. So 2t minus 1 times another 2t is 4t squared minus 2t. Plug these in and then multiply by 2t. And then over here, you see x plus y. Okay, we're going to add these together. That's t squared plus t, and then add those gives me negative 2. T squared plus t minus 2. And you're multiplying by 1, which doesn't really do anything. So finally, you can combine like terms. That's 4t squared plus t squared plus t squared. That's 6t squared. There's a t plus another t. That's 2t. Minus 2t, okay, that's just 0. And then your constants, you have a minus 1 and a minus 2, which combine to give us minus 3. And there we go, 6t squared minus 3. Now, of course, if you did that by substitution from the beginning, well, let's see, w is equal to, well, that's the product of x and y. So that would be what? T to the third minus t squared minus t plus 1 plus x times z, well, that would be t times t minus 1. That would be t squared minus t, like that. And then y times z, well, there's y and there's z. So that would be t squared minus 1 times t. That would be t to the third minus t. So we've gone ahead and changed all of this by substitution, so now it's a function of t. This is no longer w of x, y, z. Now it's just w of t. Okay, well, we can do a little better than that. We can combine terms here. So that would be t to the third plus another t to the third. That would be 2t to the third. Let's see, t squared, oh, sorry, minus t squared plus t squared. Well, that's just going to give me 0, so that's gone. Let's see here, minus t minus another t minus another t. Okay, well, that's minus 3t. And then here I have a constant, and that's the only one. So that's just plus 1. So now, if I want to find d, oh, I don't know why I switched colors there. Now if we want to find dw dt, that's simply the derivative with respect to t of this function, 2t cubed minus 3t plus 1. And since this is now just a regular function of t, we can take the derivative as we would in Cal 1. Take a 3, bring it down, subtract 1 from the power. 6t squared. The derivative of minus 3t is just minus 3, and the derivative of any constant is 0. And so we get exactly the same answer. Either of those is an acceptable method. It's just a matter of following through to the end. Now this seems pretty nice, and you think, okay, well maybe I should just always substitute. It doesn't seem too bad, and I don't have to learn a new chain rule. Well, the problem is this is not the only new chain rule. After all, the section is the chain rules. Because after all, this theorem tells us what to do if we have a function of two variables where those two variables are each a function of one variable. But why are we limiting ourselves to just one variable in the parameterization? Why can't the parameterization be, instead of g of t, why can't that one be g of t comma s? Why can't h be a function of t comma s and not just t? What happens when my parameterizations are also multivariable? Well, in that case, it's a lot harder to, well, actually, it won't be possible to, generally speaking, just make everything go away by substitution. So either way, we will need at least one new chain rule. So that brings us to the next theorem of this section. Let's begin with a function of two variables, just like before. W is equal to f of x comma y. Let's let that be a differentiable function of those two variables. Okay. Now, let's say each of those is parameterized with respect to two parameters, s and t. So if x is equal to some function of s and t, and y is also equal to some other function of those same two parameters, s and t, such that all first partial derivatives exist, I guess I should say all partial derivatives of g and h exist. Then del w del s and del w del t. So you can take a partial derivative of w with respect to one parameter or the other, del w del s or del w del t, exist and are defined by and are given by del w del s is equal to del w del x del s. Notice this doesn't include any normal derivatives. They're all partial because all functions are functions of multiple variables. So we can't use a regular derivative. It's a partial derivative. Del w del s is equal to del w del x times del x del s. Here, Leibniz notation is a wonderful it's very convenient to use Leibniz notation here because it looks like these two cancel out and you're left with del W, del S. That's not really what's happening. Most of the time, these aren't even fractions. Nothing's exactly canceling, but it's a nice mnemonic. It's a nice way to help us remember. But why did we start with del W, del X? It has two variables. Okay, so we need the other one. Plus del W, del Y, del S. Okay? And del W del T is equal to del W del X del T plus del W del Y times del Y del T. Okay. All right. The proof of this is probably the shortest one of the chapter. So here I'm going to have, okay, I'll call this one number 1. And I'll call this one number 2. All right, ready? Don't blink. This will go by very quickly. All right, the proof of number 1. Let T be constant. Okay. Now, apply the previous theorem. And that's it. We're done. Because after all, if we have one of our parameters be constant, then really we're only dealing with the other parameter. Okay, so then that means that our first function is a function of two variables, but our x and our y are only functions of a single variable. Oh, but we know how to do that. Go back here. When these are of a single variable. Okay, so there you go. It looks exactly the same as before, except these are now partial derivatives because we had functions of a two variable. So we had two variable functions where we simply held one constant. And then for number 2, same thing. Let S be constant. Just like when you take a partial derivative, you say, okay, I know these are variables, but for now let's hold this as a constant. Now apply the previous theorem. And that's it, we're done. All right. So let's look at some examples of using this. You'll note that we actually can do a little bit of substituting, but it still won't get us away from the fact that we need to use partial derivatives, and that this is not just an exercise of, oh yeah, let's do a substitution and we're back in Cal 1. Right? Okay, examples. Let's say we have a function sine of 2x plus 3y, where x is equal to s plus t, and y is equal to s minus t. Let's go ahead and find the two partials. Let's find del, I guess I should call this a name, right? Let's call this w. We'll call this del w, and we're gonna call this w. Okay? I'm sure at this point there's a few other names you might like to call some of these things, but we're gonna call it w. And then we note that after we denote these as functions of s and t, that means that w really, even though it looks like it says x and y, really these are functions of s and t. So I can take partials of w with respect to s, and I can find a partial with respect to t as well. All right, so here we go. The partial of w with respect to s, that's this one up here. It's going to be the partial of w with respect to your first variable times the partial of that variable with respect to s, the one we want, plus, well, there's no reason why we have to start with del w del x. We could also use del w del y. Oh, but then we're going to now multiply by del y del s. Here the idea being, look, these look like these two go away, del w del s, And over here, here's another way where you can get del W del S. And if you combine all of that, you get your del W del S. All right, so here we go. Del W del X, the derivative of this one with respect to X. Well, the derivative of the sine of something is the cosine of that something. Times the derivative of the inside. Well, we're taking the derivative with respect to X. So that would give me a 2. And since that's constant with respect to X, that would give me a 0. So really it's just times 2. So I'll go ahead and put that in the front. So there's my del W del X. But now I'm going to multiply that by del X del S. Well, the derivative of X with respect to S, that'll give me a 1 and that'll give me a 0. So just 1 plus 0 is 1. Plus, now let me take the derivative of W with respect to Y. Well, again, the derivative of the sine of something is the cosine of that something. Now I'm taking the derivative with respect to Y. Okay, well the derivative of 2x with respect to y is 0. The derivative of 3y with respect to y, well that's just the number 3. Okay? And now we need to multiply that by del y del s. Okay, well the derivative of this with respect to s, that would give us 1, and the derivative of this with respect to s would give us 0. So you just say times 1 plus 0, which is just 1. Or it should be 1 minus 0. But either way, that's just 1. All right, so there's our derivative. But now, note that this is a function of s. Okay, so here I should not be using my x and my y. I should substitute in my original, most basic parameters. I should substitute in x is equal to s plus t, and y is equal to s minus t. So here this will give us 2 times the cosine of 2x, which is 2s plus 2t, plus 3y, which is 3s minus 3t, okay, times 1, so we're not going to worry about that, plus 3 times the cosine. Oh, you know what? I can just say 5, right? 2 cosine of this plus 3 cosine of this is 5 cosine of this. So let me just start by saying 5 cosine of this, and I don't have to worry about that. Because sometimes you get so caught up with what you're doing that you forget how to add. All right, 2 cosine of that plus 3 cosine of that, well, that would give you 5 cosine of that. So now the 2x gets replaced by 2s plus 2t, and the 3y gets replaced by 3s minus 3t. And so this brings us to our result. That'll be 5 times the cosine of 5s minus t. Just like that. You may wish to try the next one. Go ahead and give this a try. Del w del t, same idea, same function. Let's see how that works out. Go ahead and give the video a pause. Give it a try, and once you're done, go ahead and unpause, and we'll go through it together. All right, so del w del t is del w del x del t plus del w del y times del y del t. Okay, here you can take advantage of the fact that you already know del w del x and del w del y. You don't need to compute those. We already had those. So that first one is 2 cosine of 2x plus 3y. And then the second one over here is 3 cosine of 2x plus 3y. And now we just need to compute these. Well, del x del t, the derivative of this with respect to t, the derivative of s with respect to t is 0. But the derivative of t with respect to t is the number 1. Over here, the derivative of y with respect to t, well, that would be the derivative of this with respect to t. With respect to t, the derivative of s is 0, but with respect to t, the derivative of minus t is minus 1. So here that's going to give us 2 cosine of this minus 3 cosine of this, which is negative 1, the cosine of this stuff right over here. 2x plus 3y. And now we can go ahead and plug in our x and our y. So that'll be negative the cosine of double x, really that's 2s plus 2t, plus 3y, that'll be 3s minus 3t. And so we'll get negative the cosine of, adding these gives me 5s, and subtracting these, 2t minus 3t gives me minus t. And there is our partial derivative with respect to t. Note that you can do this by substitution, but unfortunately it doesn't get you down to just a single function of a single variable. So while you may consider it simpler, it's still not a Cal 1 exercise. So here, I'll just do one of these. Let me just go ahead and do this last one right here. This one you just did. Let me go ahead and do that just by straight up substitution. So same question, I'm going to go ahead and find del W del T. All right, well, first of all, W is equal to the sine of 2x. Well, that's my x. It's s plus t. Plus 3 times y. Well, again, there's my y. It's s minus t. And so we're left with sine of 2s plus 3s, that'll be 5s. And then 2t minus 3t, that's negative 1t. All right, so there is our function with respect to just s and t. So now to find del w del t, what I need to do is to take the derivative of this with respect to t. That's going to be del t. It's still a partial, because notice that it has two variables. That's del t of the sine of 5s minus t. Well, the derivative of the sine of something is the cosine of that something. Now, if I want to take the derivative, I have to use the chain rule. Okay, well, now that's going to be the derivative of the inside multiplied in. Oh, but the derivative of the inside, which derivative? Oh, the one with respect to t. Oh, well, with respect to t, this one has a derivative of 0, since that's a constant with respect to t. With respect to t, this one has a derivative of negative 1. So that's going to be multiplied by negative 1, which gives us negative the cosine of 5s minus t, which, of course, is the same answer. So notice with this substitution, you still have to use the partial derivative, and you're still using the chain rule of two variables. But you may consider that simpler, right? Or not. In any event, substitution still works, but the end result is still a partial derivative, which means you can also find del w del s this way. Okay. Finally, for this section, we have one more theorem. This one, we're going to talk about the chain rule, and we're going to talk about implicit differentiation, something that we last saw in Cal 1. Well, actually, there's a few times where it shows up in Cal 2 as well. And I don't know how to spell. There should be no E at the end of that. Implicit differentiation. All right. Let's start off with the function. We'll call it f. And here we're going to use, for the sake of convenience, let's use this notation. If f of x comma y is equal to 0, if this defines y implicitly as a differentiable function of x, then the derivative of y with respect to x is given by negative the partial with respect to x over the partial with respect to y, provided that the denominator not be identically 0. Because of course if your denominator is 0, then nothing really makes sense here. Note that this will work for functions of higher variables. So here we've been looking at z equals f of xy or w equals f of xy. However, this does work for higher dimensions. If f is a function of 3 variables, if f of x comma y comma z is equal to 0, let's say this defines z implicitly as a differentiable function of both x and y, then the derivative, the partial of z with respect to x is given by negative the partial of x over the partial with respect to z. And if you want the partial of z with respect to y, well, that's going to be almost exactly the same, but this will be a partial with respect to y instead of x. Negative f sub y over f sub z. Again, provided that none of our denominators are 0. So this allows us to, instead of explicitly defining a function, we can implicitly define it. Instead of saying y is f of x, we can just put everything together and say, okay, f of xy is a constant, or is equal to 0. And here, if we have z equals f of xy, we can just scrunch everything together as a function of a single variable equals to 0. And then we can implicitly define the function z with respect to x and y, and then take the partials of z with respect to the variables that it is implicitly defined as a function of. So let's go ahead and take some examples of this. Let's have an implicitly defined function where y is a function of x, but we don't explicitly isolate one variable or the other. So here we have x squared minus xy plus y squared minus x plus y equal to 0. Here we just need this to be a 0. If it's any other constant or anything else, just go ahead and move it over here. So at the start, this has to be 0. If it's not, move everything over, then it'll be 0. Okay? Here you have y is a function of x. It's just not explicitly stated that way. Right? You say, okay, well, why don't we just state it as if y equals a function of x? Well, go ahead and isolate y there. Have fun. I personally do not want to. That does not look like a pleasant exercise to me. So here, instead of explicitly trying to define y as a function of x, we can instead just assume, hey, y is a function of x. There's the only two variables here, so we can just say y is a function of x. And now the question is to find dy dx. Here that's a normal derivative, not a partial, because here you only have two variables. One is a function of the other. Y is a function of x. So here that's just the normal derivative of y with respect to x. By our theorem, that's going to be negative f sub x, the partial with respect to x, over f sub y, okay? Where this thing over here is our f. All right, so this thing right here, this is f of x comma y. Okay, well, let's go ahead and do that. The partial with respect to x is, all right, well, let's see, the derivative with respect to x of x squared is 2x. The derivative with respect to x of negative xy is just negative y. And the derivative with respect to x of y squared would be 0, because it's a constant with respect to x. Okay, so I can write plus 0, but I think I'll just not write anything. Same thing for this one. The derivative of this one would also be 0. The derivative of minus x will give us minus 1. So we're taking the opposite of that over. Now take the derivative of this whole thing with respect to y. Okay, well that'll be, the derivative of this with respect to y is 0. This one with respect to y leaves me just the coefficient minus x. The derivative of this one with respect to y is, well, just take your 2, bring it down, subtract 1 from the power, 2y. Here the derivative of this with respect to y is 0, since that's a constant with respect to 0. And finally the derivative of y with respect to y is just the number 1. Here we can go ahead and distribute that negative, and that's our result. The derivative of y with respect to x is negative 2x plus y plus 1 over x minus 2y plus 1. Oh, sorry, that should be a negative, right? Negative x plus 2y plus 1. There we go. So here we just distribute our negative, and in our denominator, just leave it alone. And of course, there's other ways you can rewrite that. You can multiply the top and bottom by negative 1. Otherwise, that's a perfectly good answer. So this allows us to perform implicit differentiation of a function without having to explicitly define y as a function of x. We saw something like this in Cal 1, albeit it was a bit more complicated back then because, well, back then we didn't have this available. We didn't know what partial derivatives were. All right, go ahead and give this a try. Let's have the function x plus sine of y plus z equal to 0. So here, this is z is a function of x and y. It's just, it would be kind of hard to isolate z here. Not that it's impossible, it's just arc functions. Right? You would end up with z is equal to the arc sine of x minus y, which does not sound pleasant to differentiate or work with in any way, really. So instead, we can go ahead and use implicit differentiation. All right. Instead of saying z is equal to f of x comma y, we went ahead and just brought this over here, and we're left with f of x comma y comma z. And since we bring that over, the other side is equal to 0. Same idea. Okay, so now we can take the partials. Now remember, this is a function of x and y. So you don't look for a partial with respect to z. Here you're only looking for a partial with respect to either x or y. So let's ask for both. Let's find the partial of z with respect to x. And then let's go ahead and find the partial of z with respect to y. Given our theorems up above, it's just a matter of finding these partials and dividing out. Right? So here that would be del z del x. That would be minus the partial of f with respect to x over the partial of z with respect to x. The partial of f with respect to z, rather. Like that. And then over here, if I wanted the partial of z with respect to y, that would be negative f sub y over f sub z. So go ahead and give it a try. Pause the video, give yourself the time you need, and once you're done, go ahead and unpause and we can confirm that together. Alright, so we're going to go ahead and take the partial with respect to x. Alright, well, with respect to x, the derivative of this is 1. And with respect to x, the derivative of this is 0. Notice, there's no x here. This is all constant. Okay, so the derivative of that is 0. 1 plus 0 is 1. Over. Now we want to take the derivative of this with respect to z. Okay, well, there's no z here. That's just a constant with respect to z. So that means that derivative is 0. Now this does have a z. Okay, so the derivative of the sine of something is going to be the cosine of that something. But now we need to take the chain rule, take the derivative of the inside, the derivative of y plus z with respect to z, well, and that would be 0, since it's constant with respect to z, and this would just be the number 1. So here that would give us negative 1 over the cosine of y plus z. To find the partial of z with respect to y, note that does have the same denominator, so let's not worry about refinding that. That's just going to be the cosine of y plus z. That's our denominator. But now our numerator will probably be different. We're going to take the negative of, we want the derivative with respect to y of this expression, x plus, implicitly defined function, x plus sine of y plus z. Okay, well, the derivative with respect to y of x, well, that's 0. That's a constant with respect to y. So that means that the derivative of the constant will be 0. Okay, so plus. Okay, so we're just going to worry about this part. We can write 0 plus this, but writing 0 plus doesn't change anything. So we'll just worry about this part. The derivative with respect to y of the sine of y plus z, well, let's see, the derivative of the cosine of sine of something is going to be the cosine of that something. But now, by the chain rule, we need to multiply by the derivative of the inside. So here we're going to take the derivative of y plus z, again with respect to y. With respect to y, the derivative of y is 1. With respect to y, the derivative of z is 0. Okay, so 1 plus 0 is 1. Notice these are exactly the same, so they'll divide out, leaving us just our minus 1. So it looks like the partial of z with respect to y is minus 1. And those all make us happy. So that brings us to the end of this section. If there's any questions, comments, or problems, please make a note of those, reach out, and I'll help you guys as quickly as I can. I hope everyone has a nice day.